Why not present this one last as far as designs go, because it's weird, it's just different. Whereas the hierarchical, even though they suck, makes some sense. Okay. We've discussed procedures for dealing with a nuisance variable. Remember, a nuisance variable is something where we know it's going to cause, it would cause variation. We can measure it and remove it. What do? We block on it. Right? The randomized block design takes care of this. Piece of cake. Or as they say in Quebec, morceau de gâteau. No, they don't. They really don't. You can do repeated measures, would be another way, right? Which is a special case of the randomized block design. Also doable. You can also do something that we won't talk about in this course, which is if you can measure something and you can't block on it, you can do something called ANOVA, analysis of covariance. It's like doing analysis of variance and then statistically controlling for something. So you actually remove variance due to some nuisance variable, but you do it statistically, you don't do it with design. So there is something called ANOVA. It's something, if you go to graduate school, you might run into it. You may run into it if you do your honors thesis and say, I think this is, most of us, again, would steer you away from doing something like that. Design control is always better than statistical control, as far as I'm concerned. Okay. All right. What if you have two nuisance variables? Well, then I think you should probably just quit. Or perhaps there's a design that this little mini lecture can tell you about. So now you have two nuisance variables and a third variable, the independent variable, the thing you're actually interested in, to deal with. So 3. Well, what you do is you gotta kind of put them together. So you put them together. You probably learned about Latin squares in design and analysis, right? 2127. Did you learn a little bit about Latin squares in that course?
Just a little.
It came up, yeah. I mean, not about the analysis, but about the design, right? Yeah. So it comes up. Put the nuisance variable in a row like you always would, and put the other one in columns and in exclamation points. I am so bored right now that I had to put those exclamation points in just to wake me up. That's for a sense of completeness that I want to talk about Latin squares. I really don't want to talk about it. So this is something one could do. And now and then, I will say that of all the honors theses, for example, I have supervised, there was one person who used a Latin square. And it was because she was doing, it was a thing, it was a complicated, really cool experiment actually, and she worked with me, Jen Sushro, don't think that's her name anymore, I think she got married, changed her name, whatever. But anyway, she did a thing where she had, could people detect odors of poisons? Which is cool, right? So she had different things that were toxic at small levels, like things like airplane glue and gasoline and contact cement and all that kind of stuff. And then could you mask them with pleasant odors? Banana and cherry and all this vanilla, rose water. It was nice. It smelled great in here when she would run the experiment. But she had 8 and 8. And then she had, and there was another variable. It was the order they were done in. So she said, I said, you want to do an 8 by 8 by 8? How many subjects do you think that is? And she said, I can't do that in my head. I said, I can. We'll need 256 subjects to have one subject per group. No, I don't think we're doing that. How about we get 16 subjects and we do a Latin square? And she's the only student I ever had that didn't call me Dave. She always called me David. It sounded like Cheryl was talking to me. Well, okay, David, she said to me. I said, okay, well, let's do that. And we did. It was a really cool thesis, by the way. Because we kept saying, well, do we have to have 8? And it's like, we looked at it, it was really bizarre. I was like, yeah, let's do it, what the hell? So we used the Latin square. So this actually does come up. It's rare, but it comes up. So you get something like that, like the way that came in. So you've got, this is a nuisance variable in the rows. This is a nuisance variable in the columns. And A, B, C, and D are different levels. I know this is annoying. This is the way people do it. A, B, C are different levels of your independent variable. There's not an A, a B, a C, and a D. There's just an independent variable. It's the treatment level, we call it. And for some reason, it's always done like this. And why, I do not know. But I like to do things the standard way things are done. Move that over there. So A, B, C, and D are not a factor. They are just levels of the independent variable. Okay. Notice that each level, A, B, C, or D, occurs in each ordinal position once. And each row and column has each level once. So in this case, we would have if we wanted to do this as a full-on three-way factorial design, we would have a 4 by 4 by 4. So we would have 16. We'd have 64 groups in this case. It's not going to happen. We need 64 subjects just to test one subject per group, and those kind of designs are evil. So instead, what we have is we now have just 16 people. And I should say, actually, Jen's was 64, not 16, because it was 8 by 8 by 8. So she had 64 people she's tested instead of 16, 64. So I think that's 256. No, 512. Wow, we're going to do that. So each row and each column has each level once. Do you understand the design? I know it's a weird looking design, but it's not a bad design. This one is something one can do under very specific circumstances. I would never suggest doing this, except, like, again, there was one time when it made sense in my whole career. I don't know how many honors theses I've got to figure that out. Jeez. It's probably pushing, it's getting closer to 100 than it is to 50 honors theses I've supervised. And one time. So one time. Okay. So again, questions on the design. Does the design make some sense? Okay, good. You need equal number of rows, columns, and independent variable levels, which is it's quite a, what do you call it? It's quite stringent set of assumptions. And your model looks like this. Any score, so it's x equals mu plus alpha plus beta plus gamma plus epsilon. Any score equals the grand mean, of course, plus rows, plus columns, plus the independent variable. That's the treatment instead of the gamma. That's the treatment. Of course, plus error. Sometimes in this case, you see error just called residual. In fact, in a Latin square output, you almost always see it called residual. It's called a Latin square because the Romans used to do a thing with numbers that they liked with these squares. It's like Sudoku, whatever it's called there, that thing. Sudoku. See, you guys all know that, but you can't pay attention to this and follow it. But, kidding, I kid, because I love it. But, that's really, sometimes these are so just for me. That refers to a TV show that was on before everybody in this room was born, almost certainly, except for me. But the important thing to know is that the Romans did this, and they liked playing with numbers, but they had that stupid number system with the X's and the I's and the V's and the C's and the L's and all that. They didn't have decimal numbers. But they liked doing these kind of, it was like a puzzle. It was called Latin square. So the ANOVA looks like this: rows, columns, independent variable, residual, and total. There are P rows, P columns, and P levels of the independent variable. So in our case, you got 3, 3, and 3, so that's 9, and then 6, right? Because 3 minus 1, 3 minus 2. Oh, sorry, 4 minus 1, 4 minus 2, right? 3 and 3 and 3 and 6 is 15. Oh, and there's 16 observations. Nailed it. And you divide the mean squared for independent variable by the mean squared for the residual. You don't care about rows and columns, just like you don't care about blocking. You just want these to be nice big. When the mean square comes up for rows and columns, it's nice if it's a big number because it means you took out a lot of variance. So yeah, Jen did this and it worked really nicely. So this one, I don't think you should avoid it. I'm saying it's a pain to set up. Because one of the things you have to do when you do a Latin square, there's a whole bunch of different possible Latin squares. Like I showed you one for a 4x4 where I put A first, and then A second in the second row, and A third in the third row, and A 4 in the fourth row, but that's just one possible. So one of the things you have to do is randomly select what 4x4, or 5x5, or 3x3, or whatever Latin square you want to use. You wouldn't do a 3x3. Probably. Anyway. So what you do is you choose, you go, and there are tables literally of these things, and there's now, of course, tools on the internet. You just go and you say, generate me a 5x5 by 5, a 5x5 Latin square. And it just says, here's one, and you got it. There are, in fact, books that are simply tables of Latin squares. They are not page turners. No good character development. There's no romance in them, no action. Just Latin squares. You could actually do 2 Latin squares. What if you had 2 4x4s? Then you get a really weird thing in here. You get a between square mean square. Or you can do a cube. That means you have to have 3 nuisance variables. Those things only show up as hard questions on graduate level statistics final exams. We had one like that. We had a cube, and then we had to do between cubes. One of the cubes wasn't complete. It's like, oh, this is really useful. Hard. So one can do these things, but typically you just do the regular old Latin square. Conclusions about Latin squares. These actually can be useful if you meet these stringent assumptions. And they're totally cool. There's nothing weird about interpreting them. You can look and go, independent variable, I got that, that's easy. Like I said, Jen did it, and I think Jen probably had the best mark of any thesis student that year. In a pretty strong year, by the way. She has no speech time. There can't be any interactions. Did you note there's no interaction term there? Now, what happens, remember what the model is for this. It's x equals mu plus alpha plus beta plus gamma plus epsilon. Alpha and beta are rows and columns. What happens if there's actually an interaction? Actually an interaction between rows and columns. You just don't know it. What's going to happen? Where's that variance going to go? Well, it's not going to go to rows, it's not going to go to columns, it's not going to go to it's going to go to error. You don't want any, you want error small because you're dividing by error. Makes the F value bigger. So it actually makes it more conservative, which is good in a way because you don't make an idiot of yourself and say, it doesn't make it more likely for you to say there's an effect when there isn't one, but it does make it harder to find your effect if it's actually there. So there's no interaction. How do you know if there's an interaction or not? Can't. Remember randomized block? You could block it, you could graph it out and go, oh, I see, I think the lines cross in those 2 blocks. There's an interaction here. It's just going to make it a little harder. I'm violating the assumption. If I find an effect, I'm okay. If I don't know that maybe it's because I violated the assumption. In this case, that's not going to happen. You can't graph this out. You'd have 16 points, let's say, for a 4x8. Well, how do you graph that? I don't know. So that's annoying. So you can't have interaction. So how do you know if there's no interaction? Previous research. Go read the literature. That's all you can really do. That's all you can really do. So equal number of levels of rows, columns, independent variable will tell you you have a lattice square. Is something where you can use a lattice square. So these aren't bad designs, lattice squares. They have these really tight assumptions. And when something has really tight assumptions, usually that's an indication that it's going to be difficult to, it might be difficult to interpret. It might be difficult just to even run the experiment. Questions about lattice squares? All right. I'm very tired.
I'm very tired.
It's the time of year. All right. There's that.